Hello, welcome to the National Academy of Mobile Electronics. My name is Mike Breault, and I'm the director here at the Academy. Our goal here at NAME is to help bring quality training to the mobile electronics industry that is both comprehensive and affordable. As an installer in the industry for over 17 years, I cannot stress enough the importance of keeping your reputation intact for doing high quality, fundamentally sound installations. My motto is, do it right the first time, every time. If you adhere to this philosophy and keep an open mind to always strive to learn something new every day, you'll always be a success in this industry. Now, let's get on with our training. Sound. According to Webster's New American Dictionary, sound is defined as 1. The sensation produced in the organs of hearing by certain vibrations in the air, and 2. These vibrations, any auditory effect. In this video titled Autosound, we will show you how sound is affected within the hostile surroundings of an automobile. We'll discuss how to predict its response during the installation of our audio components to create a realistic listening environment. Let's start by previewing the various topics which we will discuss throughout our training. Our first section takes us through automotive acoustics, beginning with the refresher course on acoustic theory. Next, we'll talk about resonance, constructive and destructive interference relating to sound waves, and finally, standing waves. In Section 2, we will discuss transducer and enclosure theories, starting with the loudspeaker, which will carry over into teal small parameters. And then we will discuss several types of enclosures which you may choose to design for your audio system. In Section 3, we will cover crossover theory and how to dedicate frequencies to your various speakers. We'll also discuss the passive network and basic formulas to design 6 decibel per octave crossover networks. In Section 4, we will go over phasing, alignment, and placement. We'll discuss the benefits of coupling and define near-field acoustics and proper loading techniques. Our final section in this video covers system design. In this section, we will discuss the soundstage, rear fill, and subfrequencies, and how to utilize each segment of the listening environment to design an acoustically pleasing result in the automobile. We begin with the automotive acoustics section and a refresher of acoustic theory. As you recall in our enclosure design video, we discussed that sound occurs at the moment any body with a greater mass than the body surrounding it is set into repeated motion. Sound wave propagation is the alternate compression and decompression of air immediately surrounding an object, and then the air around the object compresses itself. These sound waves propagate outward in a spherical motion until the sound initially produced is dissipated or absorbed into the air. A basic sound wave is made up of 4 elements. First, there's the wavelength. Second, we have period. Third is the amplitude. And fourth is the frequency. The wavelength is the length of a distance a complete sound wave travels. To determine the size of a sound wave, simply divide the speed of sound by the known frequency. For instance, sound travels at 1132 feet per second, and if you divide that by 1,000 hertz, you can see that a 1,000 hertz sound wave is 1.13 feet in diameter. A 500 hertz sound wave would be 2¼ feet in diameter. As you can see, the higher the frequency, the shorter the wavelength. Period is described as the amount of time that is required for a single cycle of a sound wave. This period is defined in seconds per cycle and is identified with the formula that states a period is equal to 1 over the frequency. As illustrated here, you can see how a 20 hertz tone will cycle 20 times in 1 second. Now, amplitude is the measure of how much pressure is being put forth. The higher the volume, the higher the pressure. Here we will demonstrate a 100 Hz tone with varying volumes. As you can see, the louder the volume, the greater the amplitude. Now, when dealing with frequency, this is described as the number of cycles that pass a given point each second. Or in other words, how many times the air is compressed and rarefied each and every second. In comparing sound waves of different frequencies, you can see how higher frequencies are obviously smaller than lower frequencies. Let's look at a combination of sound waves that make up sound. This demonstration should give you an idea of just how amazing a loudspeaker truly is. Different types of sound have varying frequencies. Let's look at this graph, which will give us a better understanding of where certain frequencies lie within the spectrum of human hearing. Now, the rate at which sound is measured is in a unit called the decibel, and decibels in sound pressure level, or dB/SPL, is the acoustic measurement for sound energy. The human ear can detect changes in sound pressure in increments of 1 decibel, and it takes an increase of 10 decibels for sound to be perceived as twice as loud. Let's examine this a little closer. In order to increase sound pressure level 3 decibels to a given sound, one of two things must occur. Either double the amplitude or electrical power to your system, or double the speaker surface area. For example, if this system, which is comprised of a 50-watt amplifier and two 6-inch speakers, has a maximum output of 90 decibels, then to increase the volume to 93 decibels, we must either add 2 more 6-inch speakers or double the power to 100 watts. Now, to double the perceived volume to a system, we must multiply our power by approximately 8 times. 50 doubled is 100 for an increase of 3 decibels. To 200 watts brings us to 96 decibels, and 400 watts takes us up to 99 decibels. So as you can see here, it takes more than 8 times the power to a sound system to actually double the volume output from that system. Now, sound as it relates to distances has entirely different characteristics. If we measured a sound from a set distance, then moved away from that sound by twice the distance, we would notice a 6 dB drop in sound pressure level. The same holds true for moving closer to a sound. If we halve the distance from the point of origination, sound will gain in amplitude by 6 decibels. Using this sound pressure level meter, let's put this theory to the test. Here we have measured out distances from 1 foot to 4 feet from this loudspeaker. Let's start out by setting our microphone at 2 feet from the distance of our loudspeaker. Next, turn your system on using either pink noise, such as what's heard here, or a set tone, such as 1000 Hz or so. As you can see, we are reading about 76 decibels on our sound pressure level meter. Now, without adjusting your volume, move the microphone to 1 foot marking. As you can see, we are now measuring 82 decibels, which is a 6 dB increase. Now, move your microphone to 4 feet, and you'll notice a reading of 70 decibels. As we've demonstrated, volume does change in doubling or halving of distances in 6 decibel increments. Now, let's talk a bit about constructive and destructive interference. As we discussed earlier, sound propagates from points in cycles of waves in which compression or rarefaction occur in the air. When two waves come together to enhance the sound performance, this reinforcement of the wave is viewed as constructive wave interference. However, when two waves come together in such a way that the positive and negative phase negate one another, this is known as destructive wave interference. Phasing is critical in this area of speaker placement, and we will cover this in more detail in Section 4. Resonance is another factor that weighs heavily in the design of both a loudspeaker and an automotive audio system. Whether you consider it or not, resonance plays a big role in the success or failure of your system. Resonance is the natural ability that all objects possess to vibrate at certain frequencies. In examining the frequencies at which a normal-sized sedan will resonate, we find the vehicle will vibrate at 53 Hz, adding to the system's overall output or possibly masking sounds at these frequencies while driving. Next, using the same configuration and doing the same inside a van, we see that the resonant frequency is lower at 44 Hz. As you can see, the larger an object, the lower its resonant frequency. Let's keep this in mind when designing our system later on in the video. Our last topic of discussion before we move on to part 2 is the standing wave. The term standing wave is defined as a resonant condition that is created when a sound wave is reflected from a perpendicular surface and creates a constructive reinforced wave. Standing waves generally occur at the reflective surface equal to a multiple of half the wavelength of the sound wave itself. For example, if a speaker is 3 feet from a perpendicular surface, then the standing wave would form at approximately 188 Hz and multiples of half that and double that, or 94 Hz and 376 Hz respectively. Now the problem with standing waves, whether it be in an enclosure or inside the cavity of a vehicle, is the inability to control and suppress such waves. The formula for determining the standing waves is standing wave is equal to the speed of sound divided by 2 times the distance of the reflective surface. We will now move on to section 2 and cover transducer theory and its various characteristics. As we stated earlier, the loudspeaker is truly an amazing electromechanical device. In fact, it uses both electrical and mechanical energy to reproduce acoustical energy. In our enclosure design video, we completely dissect the loudspeaker and define teal small parameters. So for the purposes of this video, we will cover the prerequisites of the two topics to help you better understand their role in the acoustics of an automobile. A loudspeaker is nothing more than a motor which operates with AC voltages. As we showed in several of our earlier videos, when voltage is applied to a coil, a magnet is created. While the stationary magnet of a loudspeaker creates magnetism in the magnetic gap between the pole piece and the magnet. This magnetism is what is used to repel and attract the voice coil when currents alternate through the voice coil. Now the voice coil is centered into the magnetic gap using a spider, which also acts as a hinge for the diaphragm along with the surround of the loudspeaker. The basket is the housing which supports the entire makeup of a speaker. Flexible braided strands attach the voice coil to the basket, and a dust cap is used to keep foreign particles out of the magnetic gap. The diaphragm is the part of a speaker that performs the magic, starting and stopping on a dime to reproduce acoustical energy. Now, as we've mentioned earlier, larger objects produce lower frequencies, and the same holds true for the loudspeaker. It should be obvious by now that a 12-inch loudspeaker will have a lower resonant characteristic than a 6-inch loudspeaker. The teal small parameters are critical, especially when designing enclosures for your Autosound projects. The 3 that are absolutely necessary are as follows. The FS, or free air resonance, of the speaker is the frequency at which the speaker resonates in free air. The QTS is the measure of the speaker's suspension. This measurement takes all of the speaker's mechanical losses as well as the electrical losses into account to derive this parameter. Components such as the surround, the spider, and the cone material lend to mechanical losses, while the size of the stationary magnet, type of voice coil, and voice coil material lend to electrical losses. The higher the speaker's QTS, the stiffer the suspension will be. The final teal small parameter necessary to calculate a reasonably good sounding enclosure is the VAS. The VAS is the measurement in the volume of air it takes to match the suspension of the driver. In other words, how much air in a sealed cavity would it take to match the stiffness of the speaker suspension? This is generally given in cubic feet or in liters. Now, let's take a look at a few enclosures and some of their characteristics. We will begin with an infinite baffle. An infinite baffle is described as an area which will separate a transducer's front and rear wave with an infinite amount of airspace, generally greater than the area described in the teal small parameter VAS. A door, a wall, or a rear deck are good examples of infinite baffle applications. As a rule, a speaker should have a fairly stiff suspension to operate in an infinite baffle environment. For instance, a QTS of a 0.6 and above would be ideal. Next, we look at the sealed enclosure or acoustic suspension enclosure. This type of enclosure has a 12 dB per octave slope below the natural cutoff point. This enclosure will have much better transient response than a bass reflex enclosure. However, the trade-off is its inability to reach down into the lower regions of the subfrequencies. A bass reflex or tune-ported enclosure is a more efficient choice, and it offers better power handling above the tuning frequency. The rate of roll-off in a tune-ported enclosure is 24 dB per octave. A tune-ported enclosure will give approximately a 3 dB rise at the tuned frequency, since the port acts as a speaker at the tuned frequency, lending support and strengthening that frequency, such as we discussed in section 1 of our video. Two other types of enclosures that are gaining in popularity in the mobile electronics industry are the isobaric and bandpass enclosures. The isobaric enclosure basically utilizes two drivers working in conjunction with one another, as seen here, to reduce the total volume of airspace by 1/2 that is required to perform virtually the same task as a sealed or tune-ported enclosure. A bandpass enclosure is a multi-cavity and ported enclosure which uses the enclosure to filter the rate of roll-off naturally from within the enclosure. It has increased power handling capabilities and increased system efficiency over sealed or ported enclosures, and gives an increase in sound pressure level of about 5 to 6 decibels. We will now move on to section 3 and cover crossover theory and dedicating frequencies to their respective speakers. There are two types of filters we will discuss in this section: the active or electronic filter and passive filters. Let's start with active filters, also known as electronic crossovers. This type of filter is very different than its passive counterpart. However, the results are very similar. Active crossovers work by altering a full-range signal from the source before it is amplified. Let's examine this concept a little further before we discuss its benefits. All audio systems must have a source that first produces a signal, at which time it is then amplified. In this demonstration, we will start with a low-level signal such as that which is present at the RCA outputs of most aftermarket stereo systems. From our head unit, we will play pink noise from a test disc. Pink noise is a test signal which incorporates an even level of noises at the same output level from 20 Hz to 20,000 Hz. To begin with, we will first amplify this pink noise signal through the amp shown here and take a reading on our real-time analyzer. Now keep in mind the output levels that are being read on the RTA are limited to the speaker that the signal is being amplified through. Now as seen here, we are a little low on output at the top and bottom of the spectrum. At this point, the amplifier is amplifying the exact signal which is coming from the source. We will now unplug the RCAs from the amplifier, then plug them into the input side of our electronic crossover. Now this crossover has a high-pass output and a low-pass output. This is the point which the crossover takes a full-range signal and filters them. Now let's plug in our patch cords from the high-pass output side of our crossover and then into our amplifier. Now turn your system on and observe your RTA. As you can see, the crossover is sending a signal to the amplifier, passing high frequencies and attenuating low frequencies. Now unplug your patch cords from the high-pass outputs on the crossover and plug them into the low-pass output side. Now look at the RTA and you will see that the crossover is now sending signals to the amp, passing the low frequencies and filtering the high frequencies. Now in order to use an electronic crossover such as the one shown here, you must have a minimum of 4-channel amplification to accomplish this. However, since the signal is being altered before the amplification, this is a much more efficient way to design an audio system. Now a passive crossover exists in the audio chain after the amplifier, and we will now demonstrate its effects and uses. First, disconnect the patch cords from the input side of the electronic crossover and back into the amplifier. Next, we will take a large inductor which will act as a 6 dB per octave passive crossover. We will get more into detail about this later, but for now, let's hook the inductor in series with the positive side of our speaker. Since we are dealing with a pair of 6x9 speakers for this demonstration, we will add a coil or inductor to both speakers. Now let's turn on our system and view our RTA. As you can see and hear, the inductor is allowing low frequencies to pass while attenuating or filtering high frequencies. This is called a low-pass filter. Now let's disconnect our coils from our speakers and add a capacitor in series with both of our speakers on the positive side of the speaker. Now let's turn on our system and review our RTA. As we observe our RTA, we can see that caps are allowing the higher frequencies to pass while filtering the lower frequencies. Now before we move on to the terminology and formulas, let's look at one more simple configuration using passive crossovers. In comparing the high-pass filter results next to the low-pass filter results, you will notice the frequencies in which each filter allowed to pass and which frequencies were attenuated. Well, let's add our coil back in series with our speakers along with the capacitors and take one last reading of our RTA. As you can see, both high and low frequencies are being filtered simultaneously. This is known as a 6 dB per octave bandpass crossover. This type of crossover is very popular for use with mid-bass drivers in a car stereo system. Now let's discuss some of the terminology related to crossover circuits in an audio system. We will begin with the components which are vital. First, we have the capacitor. Generally, the types you will see used are electrolytic, non-polarized. However, both mylar and polypropylene are a better choice for quality results, although the cost does run quite a bit more than the electrolytic. The unit of measure for the capacitor is the farad. The caps used in our applications will be a much smaller value and expressed in microfarads. The way a capacitor works is by attenuating low frequencies. A more definitive explanation of a capacitor is an electrical component which impedance decreases as the frequency of the AC signal increases. Another marking besides the value that you will notice on the side of a capacitor is a percentage rating. This rating is generally a plus or minus 5 or 10%, which is the margin for error in the value stamped on the capacitor. More on the capacitor later, But for now, let's discuss the other component necessary for passive crossovers. As seen before, we have here an inductor. They too come in several sizes and types. Shown here is an air core and an iron core coil or inductor. You will also heard them referred to as chokes. This simple filter is measured in henries or millihenries, and the heavier the copper wire used, the better the coil. Also, an air core coil is a better choice over the iron core. However, there again is an economical decision that may come into play. The way a coil works is just inverse to that of the capacitor. The impedance through a coil will increase as the AC signal increases. In other words, the higher the frequency, the better its ability to filter such frequencies. Now, each of these electrical components that are used in a crossover network will affect the way your sound system will work. As we demonstrated earlier, each of these components attenuate frequencies at a rate of 6 decibels per octave below the cutoff point. An octave is the doubling or halving of a frequency. This being said, let's examine a simple 6 dB per octave high-pass filter. If we chose a cap that would cross our speakers over at a 6 dB per octave slope, with 5,000 Hz being the crossover point, the rate of attenuation would be 6 decibels for each octave down in frequency. So if our volume level at 5,000 Hz was 90 decibels, then at 2,500 Hz, or 1 octave down, the volume would be 84 decibels. And 78 decibels at 1,250 Hz, another octave down. Now if we had an inductor whose value filtered or had a cutoff point of 500 Hz, and again our listening level was 90 decibels, then at 1,000 Hz we would be at 84 decibels and 78 decibels at 2,000 Hz. Here's the schematic drawing for both a 6 dB per octave high-pass and low-pass filter. Now another important note to remember when dealing with passive crossovers. For every electrical component you add to your network, you will shift your speaker's phasing by 90 degrees. Now another name for a 6 dB per octave crossover is a first-order crossover. A second-order crossover will consist of 2 of these electrical components and have a 12 dB per octave slope and will shift your speakers 180 degrees out of phase. A third-order passive crossover uses 3 components and will attenuate frequencies below the cutoff frequency at 18 decibels per octave and shift your speakers 270 degrees out of phase. And finally, a fourth-order crossover uses 4 electrical components and will attenuate at a rate of 24 decibels per octave and puts the speaker back into correct acoustical phase with the system. Now when selecting a crossover point for 2 speakers, you must be careful not to select the same point for both speakers, especially when using a 6 dB per octave crossover. Let's demonstrate the problems this could create. Let's hypothetically choose 120 Hz for our crossover point for both our subwoofer and our mid-bass driver. On our subs, we will need an inductor that will pass all frequencies from 120 Hz and below and attenuate high frequencies above 120 Hz. Next, we'll choose a cap to pass high frequencies from 120 Hz and up to our mid-bass driver and filter low frequencies from 120 Hz down. As you can see, we now have 2 speakers playing the same frequency at 120 Hz. First of all, if you recall in section 1 of our video, if you double the speakers in a system, you have a 3 dB rise in sound pressure level. We also have 2 4-ohm speakers run in parallel, reducing the resistance to 2 ohms to the amp at this frequency, causing an impedance dip, and in theory the doubling of power at this frequency. And again, if you recall in section 1, we learned that doubling power will give a 3 dB rise in sound pressure level. So now we have a 3 dB peak at 120 Hz. To cure this problem, we must select crossover points that allow for a smoother transition between speakers. For instance, choosing a 90 Hz low-pass filter for our subs and a 180 Hz high-pass filter for our mid-bass drivers will help cure the peak problem at this frequency, and it will lessen the impedance dip at our amplifier. Another alternative is to use a 12 dB per octave crossover, which will attenuate the frequencies twice as fast, also curing our problem. Now let's move on to the formulas for determining the values you need for building your crossovers. We'll begin with a high-pass 6 dB per octave crossover. The formula is C equals 1 over 2 pi FCR. To determine the size of capacitor, simply measure the DC resistance of the speaker you will be crossing over and plug that in where the R is in your formula. Next, plug in the cutoff frequency you wish your speakers to roll off at. In this case, we'll choose 5,000 Hz. Now multiply 2 pi by 3.4 and again by 5,000 to get 106,760. Now divide 1 by 106,760 and you should get 0.0000937. Now move your decimal over 6 places and this will give you the value of the cap in microfarads. A 9.37 mic cap for a crossover point of 5,000 Hz using these speakers. Now let's look at the formula for determining a 6 dB per octave low pass or first order low pass filter. Here is the formula. R over 2 pi FC. Again, measure the DC resistance of the speaker to be filtered and enter that into R. Now enter the cutoff frequency you wish to cross your speaker over at and plug that into FC. Now multiply 2 pi or 6.28 by 80 to get 502.4. Now divide 3.6 by 502.4 to get 0.0072. Now move your decimal place over 3 places. To see, you will need a 7.2 millihenry choke for this crossover point. For more about passive crossovers, watch for our passive crossover video. We will now move on to section 4, where we will cover phasing, alignment, and placement. Let's begin with phasing. Phasing can be defined in many ways. However, as it relates to sound, we will define it so you may fully understand the benefits. Let's observe this loudspeaker. As this speaker goes through its movement, the air is being compressed and rarefied at different frequencies, creating sound. Now when we apply a sine wave to the sound that is being reproduced from this loudspeaker, you will notice at its starting point, through its travel forward, our sine wave climbs to its positive peak. This is the compression stage. Next, our driver begins its travel back past the original starting point to the full negative peak. This is known as rarefaction. From here, the loudspeaker returns to its starting point and begins its next cycle. This full movement from 0 to 90 degrees to 180 degrees to 270 degrees to 360 degrees is known as one cycle. Hertz are described in cycles per second. So in order for our speaker to reproduce specific frequencies, for instance a 300 Hertz tone, our loudspeaker would travel through this cycle 300 times in 1 second. If that's not impressive enough for you, think of the fact that a loudspeaker duplicates several thousands of frequencies simultaneously. Now back to our original demonstration. The positive phase of a sound wave is from 0 to 180 degrees, and the negative phase is from 180 to 360 degrees. If we have two speakers that are hooked up to where they are acoustically in phase, it would look something like this. Both speakers would go through its positive and negative alternation at the same time. Now, if the speakers were connected acoustically out of phase, you would have one speaker compressing the air while the other rarefying the air to a point that the two waves would cancel each other, resulting in a dramatic drop in volume at the frequencies which have been canceled. This is generally more of a problem with low frequencies since the size of the sound wave is so large. Now, if you recall in our crossover section, we showed you how the electrical components used in the crossovers affect the phasing of the speakers. So again, in this illustration, if we had a 12 dB per octave crossover on one speaker and nothing on the other, these speakers would be electrically in phase but acoustically out of phase. To correct this problem, we would simply reverse the electrical phase at one of our speakers. Now, if two speakers are mounted next to each other, but one is further forward than the other, the wave from one speaker will interfere with the wave from the other speaker. This occurs when both waves do not have the same starting point, and the wave will be out of phase anywhere from 1 to 359 degrees. For example, if one speaker was moved ahead 50% of its wavelength, and we used an 800 Hz tone as a reference, 1132, which is the speed of sound, divided by the frequency of 800 Hz equals a wavelength of 1.4 feet. Now half that is 0.7 feet, or 8 1/2 inches. If one of our speakers was moved ahead by 8 1/2 inches, 800 Hz would be canceled out due to the fact that they are now out of phase with each other. So it is critical when using multiple drivers with similar frequencies that you take this into account during your system design planning. Time alignment is our next topic of discussion, which may also affect phasing. As you can see here, we have illustrated a standard speaker configuration as it may be seen in a typical automobile installation. Our left speaker is 1 foot from the listener's ear, whereas the right speaker is 4 feet from the listener's ear. Now we've learned how doubling distance will create a lowering of volume of 6 decibels. So in this demonstration, the right speaker is 12 decibels lower in volume than the left speaker. Well, we can take care of that by adjusting our balance control, right? Well, adjusting the amplitude is one thing, but how do we deal with the timing problem that our subconscious can pick up? As you can see, the time delay from the left speaker is 0.88 milliseconds, while the time delay from the right speaker is 3.5 milliseconds, or 5 times longer. Now, what can we do to align these speakers with relationship to time? It's fairly simple. Simply move your speakers slightly further away to, say, the kick panels, to where the left speaker is now 3 feet and the right speaker is 5 feet. And as you can see, we've narrowed the compromise dealing with the time delay. Now let's talk a bit about placement of our drivers. Since we are talking about drivers being placed in the kick panels, let's observe how to achieve optimum results when doing this. It is always preferable to angle your speakers towards the listener to where they will receive full benefit from its on-axis response. Here is an example of the axis point of a loudspeaker. The axis is a point at which the highest amplitude from the speaker is achieved with the least amount of time delay from that particular driver. A couple of other important notes when evaluating the placement of a speaker in an automobile is to ensure an unobstructed route of travel onto the listener. As demonstrated, high frequencies, due to the short nature of its wavelength, are very directional. A knee or steering column could be the kiss of death for good imaging in an otherwise perfect sound system. Now let's talk a bit about coupling and near-field acoustics. Here we will use as an example a mini pickup truck, since low frequencies are hard to obtain due to its limited cab size. Have you ever wondered how you were able to achieve such low frequencies with a good set of headphones, but unable to duplicate that same in a vehicle? How can that be? Well, the answer is near-field acoustics. As long as the listener is within the near-field response of a loudspeaker, he will hear all of the frequencies reproduced by that speaker. Now, the area in which near-field response occurs is simply within an imaginary bubble extended off of the loudspeaker's cone, as seen here. Now, coupling can take place to extend the near-field range by simply keeping your loudspeakers next to each other, as seen here. This will improve the low frequency response and eliminate destructive wave interference at the same time. So for each woofer added beside this cluster, the further the bubble will grow. Now we will talk a bit about loading as it relates to our subwoofers. As you know by now, low frequencies have a very long wavelength, thus they become very omnidirectional. However, placing a subwoofer in the middle of a room or in the middle of your car is not always the optimum location for maximum output. In fact, by loading your subwoofer in a corner of a room, you can achieve up to a 9 dB increase over free space. The same holds true in an automobile. Here we will demonstrate how proper loading can affect the sound pressure performance of your system. Here we have a plexiglass box containing some water to simulate the cavity of your automobile. Now we will drop a rubber ball into the center of the box and observe the wave pattern. Here we will mark the highest level of amplitude created by the ball, setting the waves in motion. Next, drop the ball into one of the corners of the box and observe the wave pattern. As you will notice, the amplitude is greater when the wave originates from the corner. This is the same principle loading has with the speaker in a vehicle. Now let's move on to part 5 of our Autosound video. Here we will combine all that we have learned to design a system for an automobile. We will begin with the sound stage. Staging is created in the front of the vehicle to simulate the sound stage of a live performance. High frequencies on down to mid-bass frequencies do best when they are located in front of the listener. Frequencies from 300 Hz and up to 20,000 Hz can be reproduced with the satellites located on either side of the driver. Generally, it is difficult to set up perfect sound quality for both the driver and passenger, so when designing a system for show, this position in the vehicle is our target. Now, when locating your drivers, as we've said before, align them as correct for phasing as possible, angled towards the driver and unobstructed for best stereo imaging. It is also crucial to keep your tweeters as close to your mid-range drivers as possible and in a vertical array. Sound that is radiated from a point source gives the best stereo imagery because the separation of the acoustic centers between the two channels is optimal. Because of the close proximity of the speakers to the listener in an automobile, the horizontal array is not preferred and tends to cause a smearing of the stereo image to a point which may create a mono effect. Now that we have set up our sound stage, let's discuss rear fill. Rear speakers are installed into a sound system to add presence and to simulate the reflection of the rear walls. It is important that this sound generated from the rear speakers are not overpowering in amplitude. Generally, rear satellites consist of a mid-range and tweeter. However, the need to reproduce high frequencies up from behind the listener is not critical. It is also important to note that the human ear cannot decipher stereo images from behind, so the rear fill signal is perceived in mono. Remember that overpowering rear speakers will tend to pull the soundstage around to the sides and create an unrealistic listening environment. Next, we will talk about subfrequencies. Since we already discussed the placement preferences for subwoofers, let's discuss sound levels and bandwidths. A subwoofer or subfrequencies are generally the frequencies below 120 cycles, and most subsystems in cars today are taxed from 20 Hz to about 120 Hz. Many specialists will cross their subs over at 80 Hz and down and leave the mid-bass drivers to reproduce from 80 Hz to about 275 Hz. Now, the level of volume in any sound system will differ between frequencies based on the listening preferences of the individual. But whether you like heavy bass or prefer more treble, it is always advisable to never have more than a 20 dB swing from the bottom of the band to the top of the band. Also, always try to achieve smooth transitions between bands and avoid peaks and dips and holes in your audio system. Here are a few examples of favorable and unfavorable response readings on an RTA, and some suggestions that might correct the unfavorable readings. If you notice on an equalizer that the slide controls are all approximately 1 octave apart with plus or minus adjustments at each reading. By sliding the controls up or down, we may be able to correct problems that exist in our sound system. But remember, there is no substitute for pre-planning. Another solution for hot spots in an audio system is to add an L-pad to the speaker that is creating the overpowering response, or a notch filter at the frequency causing the problem. Designing L-pads and notch filters are a bit beyond the scope of this video, but look for them in our future crossover video. Now, let's review what we've accomplished in our Autosound video. In Section 1, we reviewed acoustic theory, wave interference, and standing waves. In Section 2, we discussed the transducer and enclosure types. In Section 3, we covered 6 dB per octave passive crossovers. In Section 4, we went over phasing, time alignment, speaker placement, coupling, near-field acoustics, and loading. And in Section 5, we covered system design and equalization.
The staff here at NAME would like to thank you for joining us in your quest to becoming one of our industry's finest. I look forward to seeing you again. And remember, your reputation begins with your first installation. So do it right the first time, every time. I'm Mike Breault. Have a nice day. Hello, this is Mike Breault again. I'm here to tell you about the many training aids that NAME offers to you as a mobile electronics connoisseur. NAME currently has 3 sets of training videos. Our intermediate set consists of basic electronics, automotive electrical, tools and safety, and installation techniques. Our advanced series consists of electrical, Autosound, security, and cellular. And finally, our Audio Architect series. It includes woodworking, fiberglass, upholstery, motorization, enclosure design, which comes with this reference guide, including several formulas, and rounding out the Architect series is the Miracle Door Panel video. NAME also offers a SpeakerCAD software, which will assist you in building enclosures, putting the tedious task of calculations at your fingertips for the following things. It will derive teal small parameters, calculate